So how can we produce standing wave in a real life? Okay, so think about just, like, let's say if I want to produce some standing wave right here at home, what can we do? What can I do? Or what could you do at your home or at his school? Okay, or what kind of things we can use and then produce this standing wave. Important thing is you need to remember there is just not one wave, there are actually two waves, right? Two waves, so they are overlapping to each other, or they are meeting each other in space. Okay, so that's the important thing, not just one wave. So think about that. Okay guys, so I got this string here, and then string, I got this motor here, okay, and then the battery. So this is an example of one-dimensional standing. It's going to be example of one-dimensional standing wave. So we have a string, and then the important thing here is this side, we are fixing, this is like fixing a boundary in this string, okay, here. And then this side I'm going to use my finger, these two fingers, or doesn't matter, whichever part of my hand, just fingers to fix the boundary here. So we will have two boundaries here. When we have two boundaries here, what happens is the wave, as we have a tension here, what happens is there is a wave, right, passing through this string, but then there is not one wave because there are two boundaries. What is happening is there is a wave starting from this end, because this one is going to be obvious in a moment, and then that wave is going to go all the way to the end here, to the tips of my fingers, and then that wave is going to reflect back, okay. So instead of one wave, we'll have a two wave, even though it started as a one wave, but because of the reflection, we'll have two waves. And those two waves, when they superimpose in space, they are going to produce, one is constructive interference, another is destructive interference. Okay, so let's see this. So this one is, I'm going to leave this, let us see. Okay. Oh, let me try to make this. It's easy to do this way, guys. Can you see? Oh, look at this. Can you see this here? Can you guys see this whole loop here? Can you see now? So see, I can also, so that's this length, right? So I can actually change the length, and then this is, so let's see. We can have just one loop here. We can have different here. We can see, try here. We can also try, look at this. Can you see? Bigger loop, right? Okay. So this is cool, right, guys? Or like this. This is harder to do, the horizontal one here, right? Oh, it can be done. Just I have to just, okay. So, but then it's possible to get different. All right. So this is an example of a standing wave in a string. Okay, so let's do pure things. Let's look at the physics. So we could have, like, so this is just a, a snapshot, right? If you take a picture of that, this is what we will get basically, right? So this is a loop there. We could also get, you know, instead of just like one loop like this here, we could also get just like 2 loops here. Here like, you know, 3 loops, 4, and so on. Okay, so we can change that. Okay. Okay, so I'm gonna draw this, you know, I'm gonna draw this demo here on the board. Okay, that's what I'm trying to do. So let's say we make this length as, you know, maybe I was using this much length, but in the board I cannot put all, so I'm gonna make it smaller. Okay, so let's say we make this length here as x. Let's call this point as x equal to 0. Okay, I'm saying one of the end is at 0 reference, right? It starts somewhere. And the other end of this, maybe I should make it a little bit down, okay? The other end of the, let me write this down, I will be more specific with what I'm going to show you. So x equal to 0. Okay, this part is at x equal to L. So basically, the whole thing is like giving me some, this L, right, length L. Okay, now since I have these my fingers in one side and then this, you know, this part here, so I'm going to make a boundary here just to show that these are the boundary. Okay, applying boundary. And then we looked at there's something called this, right? We looked at there was this. Okay, so we got this one, and this is called m equal to 1. Okay, what does that m means is mode. Okay, so m represents mode. Okay, it represents mode. Now it's not just this. Actually, if we have this length, it is also possible to have for this given length, it is also possible to have this. So here we can call m equal to 2 mode. Okay, so important way to know what is mode 1 and mode 2 is this mode, word mode refers to the number of this loop here. It may look like loop to you, but then it has a name. Okay, so this region here, this point here, this part is space, right, in between where there is a maximum amplitude, this is called antinode. Okay, antinode region, this point here. There is no point really, that's just the space with the maximum amplitude, right? Where the particle and the string are oscillating at highest amplitude. This point here, where the particle, right, these are bounded right here. And then in this case, it's this point here, where it looks like as though the particles are not oscillating at all. These points are called node, okay? So important thing, node and antinode are produced when there is a standing wave in a string here, okay? Then node represents this point where the amplitude of the oscillation of the particle is minimum. Antinode is a, you know, space where the amplitude of the oscillating particle is maximum, okay? So we can say this mode refers to the number of antinode we have in the wave, okay, in the standing wave. So here we have only one antinode, so this space, look at this space, that is m equal to 1. We have two hole here, right, like two, not hole really, two space here, right, the antinode, so m equal to 2. And then it's also possible here to have okay, so now we have 3 of these space here, right, like so m equal to 3 and so on, okay, and so forth. So you see there is, so mode 1 corresponds to 1 antinode, mode 2 corresponds to 2 antinode, mode 3 corresponds to 3 antinode, and so on. Alright, So these are the possible waves, standing waves on a string of wavelength L, right? Okay, so we want to now look at this. So this whole thing is what? Whole length is now L, we know this. And then this length is L. Look at this. This looks like a wave. This is other part. So this is actually equal to lambda by 2. Okay. So this L is equal to what? Wavelength lambda divided by 2. Okay. So this is important. This length is wavelength lambda divided by 2 here. Okay, so let's look at this. So we call this is lambda divided by 2. This is for m equal to 1. So for m equal to 1, L equal to lambda by 2. Okay. Okay. Now we can. So let's write this down. Since this is for m equal to 1, let's write wavelength lambda 1 here. Is that okay? All right. So which means lambda 1 is equal to 2 times L, okay? For m equal to 2, we can write lambda 2 equal to 2L divided by 2. Okay, can you see this length? This whole length has lambda divided by 2 plus lambda divided by 2. That should give us lambda, right? Basically, so 2 and 2 gets cancelled here, right? Really, so lambda equal to lambda 2 equal to really L. Okay, so for m equal to 3, lambda 3 equal to what? Lambda 3 is 2L divided by 3. Okay, so as you see here, so basically lambda is just wavelength equal to twice the length of the string divided by number of modes. Okay, that's what we have. And then so if we keep doing this process, we can find the common pattern here where lambda m, wavelength of the mode m, equal to 2L divided by m. Okay, so this is m, right? Value of m. So this equation gives the wavelength of standing wave for mode m, in a string of length L. Okay, so you see lambda m equal to 2L divided by m. Okay. Okay guys, so standing wave on the string can exist only, this is important, it can exist only when wavelength of the wave is given by this equation. So wavelength has to be multiple of 2L by m, okay? Otherwise standing wave cannot exist. So it has to be a multiple of wavelength given by this equation here for standing wave. Other wave are fine, but to get this, to have the standing wave, the wavelength of the wave must be multiple of this wavelength here given by this equation. Okay, so this is important. Now since we have this, since not every wavelength can produce standing waves, there are frequencies associated with, there are only certain frequencies which are allowed to form a standing wave. Okay, so those frequencies are what? So Fm equal to what, right? So those allowed frequency for a standing wave are what then? We know the relationship B equal to what? F times lambda, right? So instead of now f, we have fm, so what we could do is fm equal to what? B over lambda m, okay? And then b is just v. In place of lambda m, we can just substitute with this 2l by m, and then when I do that, b equal to what? 2l by m, right? This one. And then when I want to write it neatly, then this becomes like this. Fm equal to m times v over 2l, okay? So these are the waves which has this, which has these frequencies. These are the only waves that are allowed for forming standing waves, okay? Okay, so the frequency, there is a special name. So frequency associated with this m equal to 1 is called fundamental frequency, okay? Actually, I have a, let me show you guys this. So, just I got a pretty picture here, that's my drawing here, right? So, this F1, right? So F1 is the frequency corresponding to mode 1. The frequency that corresponds to this mode is called fundamental frequency or first harmonic, okay? So that's the name, fundamental frequency or first harmonic. So Fm means just the frequency of a higher order harmonic, okay? Now there are these names here. So first fundamental first harmonic corresponds to this, right? First overtone, second harmonic corresponds to this thing, okay? So let me write this down. So harmonic, number of harmonic equal to number of mode, okay? Mode 1 means first harmonic, okay? Now number of overtone, number, it's probably I should not write this, but so look at this number of overtone. So this is the first overtone, okay? So this is a first overtone. So how do you kind of find out which is a first overtone? What you do is, here you are looking at this one space here. When you are looking at the number of overtones, just look at this node in between. Forget about the node on the boundary, but how many nodes we have in between this, cross section, that point, that will tell us how many overtone we have. Okay, so this is a first overtone. This has what, 1, and then 2 of those two of those node points. So this is going to be associated to second overtone, third harmonic. Okay, and so on. Okay, remaining part will continue in another video.